Hi, welcome back to the Calculus 1 lecture series. And we are in the unit number 3, applications of differentiations. And this is our second video for the lecture number 22, the summary of curve sketching. So how do we, graphing our functions here? Okay, so on the video number 1, I gave you a list of some guidelines and when you try to graph the function and some of the key points to consider. Then we also did one practice to see, if the information was given, then how do you graph it? Okay, so now let's go ahead and continue to take a look at our second example here. Okay, so from the video number 1, like in here, so we did is I give you a few points, the guideline, what you need to consider when you graph. And then we also try to practice one problem, even we don't really know what the function f of x looks like, but we based on those information, what is our graph looks like here. Okay, so now for the second example here, we are going to start to work on is, if for a given function, how do I graph it? Okay, so let's go ahead and get started here. All right, so basically, let's try to follow the general guidelines I provide on our first video to see what type of the information we can have. Okay, so let's take a look at the first ones here. Okay, so the first one is the domain. So where is this domain here? So for the domain, this is a fractions, right? So we say everything except the denominator cannot be equal to 0, right? So we said the denominator equal to 0 is x squared minus 4 equal to 0. That means x equal to 2 and x equal to what? X equal to 2 and what here? The x equal to what? -2, right? So 2 and the -2. So the domain is all the real number except x equal to 2 and the -2. Okay, so that means in here, this is 1, 2, 3, 4, 1, 2, 3, 4. That means in here, the 2's here, you cannot have values there, all right? So that is the first things. Okay, so the next things here, let's take a look. Do we have any intercept, right? So the x-intercept is y equal to 0, correct? So x-intercept is y equal to 0, and my y is equal to 1 over x squared minus 4. So we know a fraction, if equal to 0, that means the numerator has to be equal to 0, and the numerator is 1. So we said y never be 0. Right, so never be 0, never be zeros here. That means no what? No x-intercept. Okay, so that means no x-intercept. That means your graph not going to passing through the x-axis. Okay, and now let's take a look at what is the y-intercept. Okay, so y-intercept is what? Is x equal to 0, right? So now the x equal to 0, you will get y equal to the -1/4. Oh, I do have an intercept at -1/4, right? So this is my y-intercept. Okay, so if you mark it, so that means in here, let's try to mark it. That means in here, you're going to touch here, right? Okay, so if this is the 1, 2, 3, 4, so it's a -1/4. So here is you're going to pass in that one. Okay, so far so good. Okay, so now let's take a look at what other information I can get. Okay, let's see if this function is an even or odd function. So you said the f of the negative x is equal to 1 over negative x to the square minus 4. So this is equal to 1 over x squared minus 4. This is equal to f of x. So what type of the function this one here? So this one is an even function, right? So I know this is an even function. And we know what is the even function mean. That means whatever the graph are going to be symmetric to what? Symmetric to the y-axis here. So I can just plot the one side of the y-axis, and then I can use the symmetrics here. Okay, now let's take a look. Do we have any asymptotes here? So the asymptote is limit x approach to the infinity, 1 over x squared minus 4. So when the limit x approach to infinity, the bottom going to be big, very big, right? So this will approach to 0. So the same way, so the limit x approach to the negative infinity is because the x squared, so still will be positive infinities here, so still will be 0. So the x, so the horizontal asymptote, I only have x-axis is my horizontal asymptotes here. Okay, and now let's take a look at the vertical asymptote. Remember, the vertical asymptote is where the denominator cannot be defined, right? So I know the limit x approach to 2. Okay, so if x approach to 2 from the right hand side, so x squared minus 4 over 1. So x approach to 2 from the right hand side. So x squared is always a little bit bigger than 4. So it's always get the positive zeros here, right? So what I have, I'm going to have here, so the x squared minus 4. So this one's here, I'm always going to get what? I'm going to get the positive infinities, right? So the same ways here, if limit x approach to 2 from the left-hand side, so this is x squared minus 4. So x squared is always a little bit less than, so it's negative infinity. Okay, so from here, I know, so here's the 2's, right? So I know I can put a dot here. Okay, so this dot here. Oh, okay, so make sure I do this dot correct. Those are my asymptotes here. Okay, so that means now in here, right? So if you approach to the from right hand side, that means here going to go to infinity. From the left hand side, here going to go to the negative infinity here. Okay, so now let's take a look at what happened to the limit x approach to the negative 2 from the right hand side. So if the x approach to the negative 2 from the right hand side, right? So negative 2 from the right hand side, that means always, you know, when you squared it, always going to be a little bit less than. So you get the negative infinity. Then here, this is x approach to the negative 2 from the left hand side. Okay, so this is approach to the negative 2 from the left hand side. Then when you square it, this will always be a little bit more than the 4. So this will give you the positives, right? So that means I know the negative 2 here. So based on these things here, let me temporarily mark it, right? So when I approach to the negative positive 2, going to go like this. And if they approach to here, going to go like this. Then in here, from the approach to negative 2 from the positive side, so it's going to approach to the positive like here. And then you approach to the, I'm sorry here, so this one's here. So you approach from the the positive, you're going down here, right? So you go down here, then you approach with the -2 from left-hand side, you're going to do here. So you kind of already know, those are be the asymptote you kind of grow up, and then later we'll fine-tune it, okay? So let's basically give you what is the graph going to kind of looks like. Okay, so now let's take a look at the critical point and the inflection points here. Okay, so now the f of x here is equal to 1 over x squared minus 4, right? And so easier to take the derivative, you can say this is x squared minus 4 to the what? -1. Then you will say, okay, let me take the first derivative. So it's f prime x. So this is, you move the -1s here. So this is x squared minus 4, then the -2, then the chain rule 2x, correct? All right, so in here, then you will get the -2x, and this is x squared minus 4 to the -2, +2, I'm sorry here. So this is a +2, you move to here is a +2. And then we know the derivative is, the critical points defined is first derivative equal to 0, right? So first derivative equal to 0, that means x has to be equal to what? Equal to 0s here, right? So this will be one of my critical point. And then we also said it's undefined. So x equal to -2 and 2, but those two are not in my domains, right? So those are the undefined. So this 2 is not the critical points, right? So the only critical point will be x equal to 0 here. Okay, now let's try. Okay, so now we need to see the increasing, decreasing here, right? So let's try to do this. Okay, so this is my 0, and I know in the 2, this is not defined, right? So I mark here, this is not defined. Okay, so take a look at f prime x here, right? So when the x is greater than, when x is greater than 0, remember the denominator is always positive, correct? X is greater than 0 is always positive. So what I have here, so this one's here will be what? It's negative, right? So the f prime x is negative. And then also like if x is greater than 2, what happens here? This is also is negative. Then let's take a look when the x is less than 0. So then there is, for example, -1. So the bottom is always positive. So we get a positive. And here we give a positive. And so remember, right? So if it's the negative, I know my function is what is decreasing, decreasing. Then here is increasing, increasing. See here. That means from 0 to the 2, my function going to be decreasing. And then from the 0 to the infinity, my function going to be decreasing as well, right? So it's my function going to be continue decreasing. Then in here, right, from the here is increasing to the decreasing. So at the x equal to 0, what I'm having here, I'm having a what? It's a local what? A local max here. Okay, so based on this information, I almost can graph it. So I know, so in here, right? So let's just see, we'll be able to graph this one. So it's, go here, right? Because we say it's going to the asymptote. So, and also because this is increased, so decreasing. So my curve is here, and here is curve is here, right? And then we also say from the 0 to infinity is decreasing also, right? So I said, okay, let me try to erase this one. It's decreasing also, right? So that means it's going to decreasing to, okay, Okay, so then in here you can sort of decreasing, and then you have asymptote, so you're going to like close to here. Then this one is increasing, right? So it's increasing here. And now the next thing is here. Also, we can say this is increasing, but with the asymptote. So probably will go like this. All right, so this probably will be my graph, but in order to make sure I need to know my concavity, I bend correctly. I could, I could have something like this, right? So I could have something like this, right? So it still is decreasing, right? So I don't know what is my concavity looks like. So that's why I still need to check to see the way I defined my concavity is correct or not. Okay, so now let's take a look at my concavities here. Okay, so the concavity will be the second derivative, correct? Okay, so now let's take a look at the second derivative. The first derivative is here, right? So the first derivative is f prime x is equal to the negative 2x squared minus 4 to the negative 2. Okay, so now my second derivative, it will be, I can use the product rule, right? So I fixed 2x here, negative 2x. Then here is the negative 2x squared minus 4. I have negative 3. Then what I have a chain rules here, correct? All right, then plus, then I take derivative of the first term, so this is negative 2, then this is x squared minus 4, and then negative 2 here. Okay, and then now if I simplify a little bit here, this is 2, 2, 2, so I have ax squared, right? And this is x squared minus 4 to the negative 3. Okay, then I have a negative 2, then x squared minus 4 to the negative 2 here. All right, so now let's try to factor out, because this is going to the denominator, correct? Negative 3. So I find the common denominators, so I will factor out the x squared minus 4 to the negative 3. So if you factor out, what happened on the first terms here, I have ax squared. So because you factor the negative 3 out, what do you have on the second term? You will have the x squared minus 4 here, right? Because you need to times one positive exponent to become the negative 2. Okay, so now in here, you can put this ones here. So this is x squared minus 4 to the third power. So let's simplify this. This is ax squared minus 2x plus 8. So what do you have here? You have 6x squared, right, plus 8. So let's see, do I have any inflection points here? F prime x equal to 0. That's the inflection point. Then we say no such x's here, right? So I don't have inflections here. And then we said, so now let's take a look at the second derivative test. So I put the double prime 0. What is your 0 here? You get the 8. Then 0 minus 4 is minus 4 to the third power, right? So you will get a negative 1, 8. So this, okay, so by the second derivative test, so I know the F0, I can have a what? So that means X0 have a local what? Local max, right? So I have a local maxima. We already from the, this graph, we already did that. So, okay, so now let's take a look here, the concavities here, right? So let's see the concavity. Okay, and I don't have any become the, the zeros, don't have an inflection point, so I still can put here, this is 0, 2, and the -2. Okay, now let's decide is it positive or negative. So here, okay, so when x equal to the positive, so the top is always positive. So between the 0 and the 2, so what is here? This is negative, right? So the greater than 0, so what is here? This is a positive. And then between the -2 and 0, what the -2 and the 0, what do we have here is negatives here, right? Then the greater than -2, what are we going to have here? The greater than, and this become the positive. So we have a positive. So this is my second derivatives, right? Okay, now we know the second derivative is the positive is a concave up. This is a concave down. This is a concave down. This is a concave up, right? So we're going to be concave down between -2 to 2 and a concave up, from the 2 to infinity and the -infinity to -2. Let's take a look to see our graph match that or not. Okay, yes, from the -2 to +2, I'm concave down. From the 2 to infinity, I'm concave up. Concave up. So I know I don't need to modify my, my curves here. Okay. So this is one of the problems. How do we do the graph? By a function, by considering all the important points here. Okay. Let's try to do one more and see if we be able to do it. Okay. So it's the same idea. The first thing is here. Let's take a look at the domain. So we know the domain natural log cannot be what? Cannot be 0 and cannot be negatives, right? So because natural log, so I know my domain has to be what? 0 to infinity. So that means it's going to be this side of the graph. Nothing going to be happens here. Okay. So let's take a look at what is the x-intercept. X-intercept is y equal to 0. That means x is going to equal to the natural log x. And we know that x and the natural log x, they never intersect, right? So like if you graph it, this will be the y equal to x, and this is going to be y equal to the natural log x. They never intersect. So there's no such x. We're going to be equal to natural log x. So we say no such x. So that means no x-intercept. All right. So that means for the graph here, you're not supposed to touch the x-axis. All right. Let's take a look. Do we have a y-intercept? Y-intercept is x equal to 0. No, cannot. X equal to 0, not in domain. Right? So x in 0, not in the domain. So there's no y-intercept neither. Okay, so it's good. No y-intercept. Now let's take a look. Let's take a look at the asymptotes here. Limit x approach to infinity. And this is x minus natural log x. So x approach to infinity, x minus natural log x. I know that x is always increasing faster than the natural log x. So the limit is infinity. That means it's no what? No horizontal asymptote, right? So they're not going to approach to some value. Okay, so let's take a look. How about the vertical asymptotes here? So let's see here. So limit x approach to 0 from the right-hand side, x to the natural log x. See what we have here. Okay, so in here, we see here, the approach to this will approach to 0, right? So the natural log, when they're getting closer and closer to 0, will approach to what? It's a negative infinity. So the whole list is going to become what? Positive infinity. All right, so let's temporarily mark it. That means that my graph is going to go something like that, correct? My graph is going to go something like that is because it's going to have the, this is my vertical asymptotes here. All right, so let's temporarily mark this trend so later we can fix it. Okay, now let's take a look at what is the critical point. So now the f prime x, so will be 1 minus 1 over x. Okay, so I will set equal to 0. So I will get x equal to what? X equal to 1 here, correct? And also x equal to 0 is not defined, right? And that one is not in the domain, so it's not the critical point, it's not defined. Okay, so now let's try to see what is my function going to look like. So this is 0, 1 is not 0 is not defined, so 1 is here. Okay, so for everything is less than 1, okay. So let's see here, for everything is less than 1, 1 minus x going to be what? Going to be negative. Am I right? Right? Everything is greater than 1, so this is going to be positive. So, okay, so first derivative, so this is our first derivatives, right? Okay, so first derivative determine the function's behaviors, increasing, decreasing. So this is decreasing, this is increasing. Okay, so now I know in here this is 1, 2, 3. So that means from 0 to 1, my function going to be decreasing, right? So it's going down. So my function is supposed to go down here, right? And then from the 1 to 2, my function going to go up, something like that. All right. So now, okay, so we kind of roughly graph it. Then later we're going to be, we'll be able to see that. And because, the going down and going up, so I'm sure what is here. So in here, x equal to 1, what is going to be here? This is going to be a local minima. So it's somewhere here, right? Going to have a local minima point. Okay, so when x equal to 1, so and this one's here, that means f of 1 is equal to the 1 minus natural log 1 is 1 here. So I know in here they're going to have local minima. Now I know I almost can see the shape of the functions, right? Going down, going up. Now the only thing I need to know is my concavity. Okay, so now here, the second derivative. So the second derivative, 1 is becoming constant because 0. So this is, so this one is negative, and then the negative 1, x to the negative 2. So what I have here is 1 over x to the squares, right? So then the 1 over to the x square, and then I know in here, x equal to 0 is not in the domain, so it's not an inflection point. So let's see here, okay, 1 and here. So you see here the x, because the second derivative is here, right? So this is my second derivative behavior. So between the 0 and the 1, so it's always positive, and 1 to infinity is a positive, correct? Is because this is always a square, so it's a positive. So based on the second derivative, I know if it's a positive, it's a concave up, concave up. So that means the f prime x is here, f double prime x is always positive. That means that the whole function is always a concave up. So now I can finally fine tune my graph here, right? So I can finally fine tune my graph, and I know my graph is going to go something like this, right? So this will be my vertical asymptote, and then going turn here, go here, right? So it's a concave up all the way here. Okay, so that's how to that's how do we the graph the function by consider those few key points here. Of course, if you want to make the graph a little bit like a nicer, you can pick up the several other points in the domain, and so they might give you, you can shape your graph to the, is more accurate layer. All right, okay, that's it. Let's take a break here, and then we will come back. Let's take a look at our last things for graphing is, do we have like the slant asymptote? All right, so that's it. Have a good day, okay? Bye.